In this video, we are going to look into pulse amplitude modulation, pulse width modulation, and pulse position modulation. These are analog pulse modulation schemes. The discussion of these pulse modulation schemes would be supported with a Simulink MATLAB based simulation environment where we would look into the modulation and demodulation of pulse amplitude modulation, pulse width modulation, and pulse position modulation. To briefly overview the modulation schemes, we have continuous wave modulation and pulse modulation, wherein in the continuous wave modulation, the context is usually the frequency translation. That is, we may have a low frequency content and we want to shift it to a higher frequency in order to reduce the antenna size or benefit from the usual features of modulation. So within this continuous wave modulation, we have linear modulation and we have non-linear modulation, and within the linear modulation, we have amplitude modulation. Within non-linear modulation, we have frequency modulation and phase modulation. The discussions related to amplitude modulation, frequency modulation, and phase modulation is given in the description below of this video. Herein, we are more interested towards pulse modulation, and the context of pulse modulation is representation of a given signal, that is the message signal, into an alternate form or a waveform for further transmission. That is, we change the waveform of the message signal for further transmission. So within the pulse modulation scheme, we have digital modulation schemes, and they include pulse code modulation, which includes sampling and quantization, and furthermore some variants of it, that is differential pulse code modulation and delta modulation, also comes under the digital modulation schemes. Discussion regarding the digital modulation schemes are given in the description of this video as well. Presently, we are interested in analog pulse modulation, and within this analog pulse modulation, we have the pulse amplitude modulation, pulse width modulation, and pulse position modulation. Note that in sampling, for example, in pulse code modulation, we often resort to a direct delta function, which is delta of t. That delta function is basically having a width which is approaching 0 and its height is approaching infinity. And hence that is not practical to create. So as a solution in analog pulse modulation schemes, we resort to rectangular functions as compared to direct delta function. That is, we would have a function of this form. Now let us consider the first case of analog pulse modulation, that is PAM. So as the name suggests, this is the simplest pulse modulation scheme whereby the message signal is encoded in the amplitude of a series of signal pulses. So the information is carried in the amplitude. The generation of PAM can be done by considering a message signal M of t. Over here we have considered a single tone signal, but you may have any signal. And this signal is multiplied with a periodic pulse train that we have expressed as P of t. Note that this periodic pulse train has a time period, say Ts, and the gate or the rectangular function is basically available over here, which takes a fraction of this time period Ts, and it has an amplitude of 1, and then it repeats at regular intervals. Now multiplying this message signal with the periodic pulse train would lead us to the pulse amplitude modulated signal, and for that we have two different types. The first one is natural PAM and the second one is flat top PAM. So note that if we multiply these two together, so we would have this signal which would be multiplied with the first instant when the gate is open. Hence this signal would be multiplied with this 1 until the duration of this gate, and this is expressed over here. So we have a curve over here which follows the message signal m of t. At this point we have this section appearing over here and so on. So this formulates the natural PAM, but we often desire a flat top PAM, and for the flat top we do not want this curve and rather we need a fixed value. So we can use a technique that is sample and hold, and we are going to pick this value which is over here and then continue it at the same value for the duration of this gate until here. So this formulates our flat top PAM. An important consideration over here is that the width and the position of pulses is the same. That is, the width remains the same for all of these pulses and they appear after the time period, say Ts. Now in the pulse amplitude modulation, so the main advantage is each pulse is valid within its allocated time Ts. So this is our Ts and each pulse is available within that. That is, we do not have this pulse interfering with the successive symbol or pulse. Now when it comes to the disadvantage of using PAM, consider that we have a channel, the communication channel, and this communication channel is time varying. So if it is time varying, due to this time varying channel, the information stored in the amplitude may change, right? So that is, if you send this signal but on the receiver side we have some sort of this behavior because of noise, so the receiver would have some difficulty in detecting what was the original message. Note that this is because the information is stored in the amplitude, so if the amplitude is varied we would have issues in detection. PAM finds many applications including its use in switching speed of LEDs. So hence using PAM we can have a high speed data which can be wirelessly transmitted to these terminal devices such as cell phones and laptops. Lastly, regarding the demodulation, we simply use a low pass filter to demodulate and get back our message signal m of t in some form. Now let us proceed towards the modulation and demodulation of PAM using Simulink. So this is our modulator and demodulator for PAM. So let us zoom on to the PAM block only, and specifically let us see the modulator first. So we are going to start with the message signal, which is a sine wave, and in the library browser we have used the signal generator, and for that we have a waveform and we have used the sine wave with an amplitude of 1 and frequency of 2 Hertz, and we feed this message signal to the scope which also can be obtained from the library browser. Next we have the pulse generator, which has an amplitude of 1, and we set the time period to 0.2 seconds and the pulse width of 25%, and then we have a phase delay of 0.1 second. So we feed this to this multiplier in the red, and the upper branch is basically coming from the message signal itself m of t. So this red multiplier, this indicates that we have a natural PAM, that is, we're just multiplying the sine wave with the pulse generator. So to understand this, so let us look into this scope of PAM. So this is our message signal m of t, and this is the pulse train p of t, which is active 25% of the time in this time period. So multiplying this and this, we are getting the natural PAM, and this natural PAM follows the message signal m of t in this gate duration. But as mentioned, we often desire a flat top PAM, and for that I have used a sample and hold with the trigger type of rising edge, and at the input we again have the message signal, and for the rising edge detection we use the pulse generator. So this pulse generator is fed to this green multiplier, and the output of the sample and hold is also fed to the green multiplier, and then this green multiplier, this output leads to the fourth port of PAM, which is this signal that is indicating the flat top PAM. So we have the two types now, that is the natural PAM and the flat top PAM. Now for the demodulation we are going to consider the flat top PAM, and this output of the transmitter which is coming out of this green multiplier is fed to a low pass filter, that is analog filter design mask link, and we have selected Chebyshev 1. Then this is a low pass filter of order 8 with 2 pi into 2.5 just above the frequency that we have selected for the message signal, and then the pass band ripple in dB is set to 2. Afterwards we have a gain of 4, and then we feed this to the PAM that we receive. So in this scope, the first is the message signal, the second is the PAM signal, whereas the third port is the demodulated or detected message signal from the PAM. So over here, this was the original message signal, this is our flat top PAM, and over here we have the recovery of this message signal. Note that in this filter we have removed all the high frequencies of this PAM, and this is the low frequency. The order of the filter would define how fast we can reach this stable point. Moreover, if you look into this point, for example over here, you can observe that there is a phase shift between this point and this point. That is, the detected message signal is little bit shifted towards right, that is, it is delayed in time. The message signal over here is at 0, whereas at 5 seconds it is less than 0, and it has a 0 crossing just after 5. Now this delay is basically again the inherent property of a low pass filter. However, this delay is consistent and hence it would lead to a distortionless transmission because all of this signal is delayed by the same unit. So this would eventually help us in the recovery. So this was about the modulation and demodulation of PAM. Now let us move towards PWM. Now for the pulse width modulation. The information is available in the width of the pulses. Hence we can also refer it to a pulse duration modulation, that is PDM. That is the width of the pulses are varied according to the sample value at particular instant of the message signal. Now when it comes to the generation of PWM, consider that this is our message signal M of t, which is expressed over here, and then we have a sawtooth signal, sawtooth periodic signal. So let us call this signal, which is a sawtooth periodic signal, as S of t. So next we take the difference of the first two signals. So we can say this is our W of t, which is M of t minus S of t. That is, we subtract this signal from this signal to achieve this difference signal. And from this third plot we use a comparator. That is, we set a threshold at 0. So whenever a signal is above 0, we will consider a value of 1, and whenever it goes beyond 0, we would consider a value of 0. So based on this comparator, we have this PWM waveform where we represent this message signal in terms of distinct widths of this PWM signal. That is, we have M of t and we subtract the sawtooth signal to achieve W of t, that is a different signal, and afterwards we use a comparator to achieve the PWM signal. So an important consideration over here is that the amplitude and the starting position of PWM signal is the same, is identical. So all of these rectangular functions within this PWM have an amplitude of 1 and their starting point is identical. After each time period we have a rectangular function of certain duration. Now when it comes to the advantages of using PWM, so we say that small changes in the amplitude because of time varying channel will not affect the detection of information pulses. That is, if we are going to transmit this waveform over the air and we have a channel and then we have a receiver. So if this is a time varying channel and we have some fluctuations in the amplitude of this transmitted wave, but since the information is stored in the width rather than the amplitude, so hence we would not have much difficulty in the reception of a PWM modulated signal. So when it comes to the disadvantage of this PWM, we know that the message signal and its amplitude determines the width of the PWM signal. So if this amplitude has a sudden surge, for example, we have a surge over here. So we would have some difficulty in detection because the modulation would be spreading to other pulses right over here. So there will not be any specific distinguishing point. So you may have, because of a surge, this pulse having an effect on its successive pulses, which would lead to some difficulty in the reception. As an application, PWM is an effective method of reducing the average power delivered by an electrical signal by effectively chopping it up in terms of the duty cycle, where the duty cycle is simply a fraction of one period when a system or a signal is active. For example, over here, this is a 0% duty cycle which is increasing, so this width would increase and so on until it reaches the 100% duty cycle, and now it is decreasing. So the amount of duty cycle or the percentage or a fraction of a signal that we are considering, that would have an effect on the average power. For example, right now the average power is maximum, and at 50% the average power would be half, and so on. And lastly, for the demodulation, we convert the pulse width modulation to a pulse amplitude modulation, and thereby we use a low pass filter for detection. Now let us move towards the simulation using Simulink for the modulation and demodulation of pulse width modulation. Now over here we have PWM, the modulator for PWM, and the demodulator for PWM in the Simulink environment. So let us first zoom in on the desired blocks. Again we have a message signal M of t, and this is a signal generator obtained from the library browser over here, and we feed it to the scope. Next we have a sawtooth wave, sawtooth generator with a frequency of 4 Hz, and then we have an add block, right, where we have set a plus and a minus. That is, in this sum block we are subtracting this sawtooth from this message signal. So the output of this subtract block is fed to the PWM scope, whereas the sawtooth is also fed to the scope in the second port. Furthermore, since we are interested in the modulation of PWM, we use a comparator block that is compared to 0 mask link, right? and we have used the operator greater than or equal to with the output data type Boolean, that is logical. And then we feed the output of this comparator to the scope. So these are the four waveforms. So let us zoom some initial points. So over here we have a message signal, and this message signal has a time period of 0.5 mentioned over here. And then we have a sawtooth signal which is over here, and this sawtooth right now it is having a time period of 0.25. that is in 0.5. Now we have two waves of the sawtooth signal. The third waveform is coming from here, which is the subtract block, that is we are subtracting this signal from this signal. So eventually we achieve the third waveform that is coming from here. And lastly, in the third waveform we use a comparator. So any value which is above 0, that is considered as 1, and any value which is less than 0, it is considered as 0. So hence in the fourth waveform, which is from the output of this comparator, we have a PWM signal. Note that within this duration, that is 0.5, we have two pulses of PWM, and each pulse is taking a fraction of the duration of 0.25. So this fourth waveform is our PWM signal. Now for the demodulation of PWM, all we need to do is to convert the pulse width modulated signal, which is over here, to an equivalent pulse amplitude modulated signal, and afterwards we can use the demodulation these blocks of PAM to recover back the message signal. That is, we need to convert pulse width modulated somehow to a pulse amplitude modulated signal, and then we will use a low pass filter, and eventually we will get back our message signal. Now in order to convert the pulse width modulated signal to a pulse amplitude modulated signal, we have these four blocks that we have used, and let us see what are these blocks. This pulse width modulated signal is coming out of this comparator, and the output of this comparator is in terms of a Boolean logic. So we use this convert block that converts the data type. So this is used in the conversion, data type conversion, which is required at the subsequent block. So in the subsequent block we have an integrator, that is continuous time integration of the input signal, and we have an external reset at the rising edge with initial conditions source as internal, and we press OK to this block. So we feed the data type conversion output to the integrator, and we again take a thread and plug it into the reset button of this integrator, which is rising edge over here. Afterwards we take the thread out of this integrator and we feed it to the third port of this PWM signal. In the meanwhile, we have this trailing edge monostable block with the edge detection as falling edge, pulse duration of 0.05, and with initial condition set to 0 and sample time to 0, and this is fed to a multiplier block. This is the product block with number of input ports set to 2. So the output of this integrator is fed to this product block, and at the same time the output of this monostable block is fed to this multiplier, and then the output of this multiplier is then fed to the PWM signal. So in short, all of this converts the PWM waveform to an equivalent PAM waveform, right? So let us see what is that waveform. Now the first waveform, that is the first value to this scope, is of the message signal. So this is our message signal over here. The second input is from the pulse width modulated signal, which is over here. This is the modulated signal that we want to convert to the PAM equivalent signal, and afterwards the third signal is coming from the output of integrator, this integrator. And what this integrator does is it is basically trying to integrate all of this area. To understand this waveform, let us zoom the waveform further. So in this third waveform, what we have is we have an integration which starts at 0, right? And it would integrate until this point, and after that the value is 0, so this integration would have a stable value. But whenever there is a rising edge in this waveform, so at that rising edge we are going to reset this integrator. So this is the property of this integrator, that we have an external reset at the rising edge. So whenever we have a rising edge, we have a reset of this integration, and then again it would increase whenever we have a positive pulse, and at 0 it would remain stable until again we have a rising edge where it would reset to 0, and then again for the positive pulse amplitude it would again increase, and so on. So this is the output of a external reset integrator block that we have used. Now to convert this signal into an equivalent PM signal, we need to chop off the undesired values, and for that we want to get rid of these values which are increasing, and we are interested in these stable values, right? So what we do is we multiply this third waveform by using this block, and what we multiply with is this monostable, right, having a pulse duration of 0.05. So whenever we have a falling edge, we are going to have a pulse duration of 0.05 second, which would be multiplied with this signal, right? So hence we would only be left with this part, and this part would be 0. Similarly, at this falling edge we would have a multiplication of 0.05 second, and rest of it would be 0, and so on. Now the fourth waveform is kind of a pulse amplitude modulated signal. Now for this signal, for the fourth waveform, then we use a band pass filter, which is expressed over here. So we have used a band pass filter to remove the DC value as well from this signal. These are the parameters. It's an 8th order band pass Chebyshev filter, and then the output of this filter is fed to this second scope. So let us plot this scope over here. So again, this is our message signal which is coming from here, and the second is the output of this multiplier, a kind of a PAM signal, and the third waveform is coming from the output of this band pass filter, which is over here, and finally we use a gain with this setting to recover back our original message signal. Now based on the order of this Chebyshev band pass filter, we would have some settling time, right? And afterwards over here you can observe that this is almost following the message signal itself with the same period. Note that the transmitted message signal over here and the received message signal is almost similar. However, there is a slight delay in the received signal, and that delay is coming from this Chebyshev filter. That is, it is an inherent property of the filter. So this is our demodulated PWM signal. Now let us discuss about the pulse position modulation. In the pulse position modulation, that is PPM, the message signal is encoded in the position of series of signal pulses. That is, the position of pulses are varied according to the sample value at a particular instant of the message signal. So for the generation of PPM, again consider that this is our message signal M of t, and as per our prior discussion, we say that from this message signal we have achieved a pulse width modulation signal, PWM signal, and from this PWM signal we invert this signal by using a NOT gate to achieve a complementary pulse width modulated signal. And from the rising edge of this third waveform we sample this value and hold it for a certain duration, and whenever it is rising again we sample and hold for the same duration. So in short, the rising edge of the complementary PWM signal is giving rise to a PPM, or more directly for the trailing edge of this second waveform. We can use that trailing edge to insert a pulse of certain duration. So whenever there is a trailing edge, we have this pulse, and the width and the amplitude of that pulse are identical. That is, all of these pulses have identical widths and same amplitude, that is 1. However, the position is basically modulating the message signal. Now, as an advantage, small changes in the amplitude because of time varying channel will not affect detection of information pulses. That is, if you are transmitting this and we have a channel and then we have a reception Rx. So if this channel is time varying, so we would have a perturbation in these amplitudes. But these amplitudes are not conveying information. In fact, it's the position which is conveying information. So hence we would not have any issue in the detection if there are some changes in the amplitude of modulated signal. However, as a disadvantage, if the amplitude has a sudden surge, that is at the transmit side, if this message signal has a sudden surge, for example over here there is a sudden surge, so we would have an issue in the PWM signal, and eventually we would also have an issue in the position of this pulse, which may affect the neighboring pulse. And an application of pulse position modulation is in terms of fiber optics and optical communication networks. Moreover, with regards to the demodulation of PPM, we convert the PPM to a PAM model, and then we use a low pass filter for the detection of message signal in some form. Now for the modulation and demodulation of PPM, we present a Simulink based simulation environment. Now for the simulation of pulse position modulation, we have the modulator and demodulator. The modulator block is over here, whereas the demodulator block is over here. So starting off with the message signal, right? This is our message signal, which is a simple sine wave. So this is single tone having an amplitude of 1 and a frequency of 2 Hz. And this is from the signal generator of library browser. And for the modulation of PPM, we would be taking some insight from the PWM. Specifically, we have a sawtooth wave with a frequency of 4 Hz, sawtooth generator from the library browser again, and then we have the addition block, that is sum with a plus and a minus. That is, we subtract the sawtooth generator from this sine wave, and afterwards we use a comparator compare to 0, and that led us to the pulse width modulated signal. Now we take the feed out of this comparator over here, and we plug it into a monostable with a pulse duration of 0.05 second, and the edge detection is falling. That is, from the falling edge detection of PWM signal, this is our PWM signal. So from the falling edge we would have a signal which is having a duration of 0.05 second. So this is the third feed to the PPM, that is the scope which is representing the pulse position modulation. The first input is that of the message signal, the second is the PWM, and the third one is the PPM. So let us visualize the PPM signal. That is, in this scope of PPM, the first signal is the message signal, which is this one. The second is the PWM, which is this signal, and from the falling edge of this signal we have a pulse of duration 0.5 second, which is yielding basically a PPM signal. So note that we have two pulses within this 0.5 seconds, so each pulse has a time period of 0.25, and the position of first pulse is very near to the terminal point, that is around 0. 0.21 to 0.23, and whereas the second pulse is at the initial or the starting point. So the position is basically adjusted as per the technique of pulse position modulation, and this continues on for this periodic signal. Now for the demodulation of this pulse position modulation, again what we need is we need to convert the pulse position modulation signal, this PPM signal, somehow to a pulse amplitude modulated signal, and for that we have used all of these blocks, and afterwards we are going to use a band pass filter along with the gain to recover back this messy signal. Specifically, from the modulated signal over here, we pass that signal to a NOT gate, that is a logic operator which is NOT, and the output of this NOT gate is fed to this scope, right? So let us open this scope side by side. So in this scope, the first signal is the messy signal, so that is this signal is a messy signal. The second is output of this PPM passed through a NOT gate. So if you pass this PPM through a NOT gate, we would have a pulse width modulated signal. This is PWM signal. And after that, what follows is that we just need the demodulation of PWM that we have done before, and which is repeated over here. So this logical operator, the output of this logical operator is passed through a convert block, that is, this is a data type conversion that is required for this integrator with an external reset rising, right, with these parameters, and the output of this integrator is the third waveform which is over here. And in this third waveform, what we have is we have an integrator which would start to integrate until this point, right? So we have a linear increasing slope. At this point, this is not increasing the area because over here the value is 0, so we have the value which is 0, and then at the rising edge of this next pulse we have a reset, that is, we have an external reset at the rising edge. So whenever we have a rising edge, we would have a reset, and this integrator would start again from 0 value, and then it would try to integrate this, which is done over here. It would be stable at this point, and again at the rising edge we would again have a value which is falling back to 0. So from the output of this integrator block, we have this waveform, third waveform, which is then multiplied with this PPM signal. So this was a PPM signal, so we take this pulse position modulated signal and multiply it with this waveform. So if this signal is multiplied with the pulse position modulated signal, so eventually we would have this fourth waveform which is over here. So at the output of this product, with having two number of inputs, we have this waveform. Now this fourth waveform is kind of a pulse amplitude modulated waveform, and we proceed towards the demodulation of that, and for that we have used analog filter design, that is band pass filter with these parameters and having an order of 8, followed by a gain. For the representation, we are feeding the output of these blocks to this scope. So let us visualize this scope. So in this scope, the first waveform is again the messy signal coming from here. This is our message signal. The second is the output of this multiplier, which was previously represented as the fourth input in this scope. But anyway, this is right now our second waveform. Afterwards, we have an output from the Chebyshev filter, band pass filter, as the third input, which is over here. And you can observe that because of this characteristic of this band pass filter, we have an initial tracking delay, and after some time we have a stable region, and lastly we have a gain k with this parameter, which is then fed to the fourth input of this scope, which is over here. So let us zoom in some of these values, and we can observe that using this demodulation technique of pulse position modulation, we have recovered back the message signal. So again, you would observe that at the 7th second we have a slight delay as compared to the message signal, and that delay is from this filter. However, this delay is consistent throughout, so basically this comes under the criteria of distortionless transmission. So this was all about the pulse position modulation. Thank you for tuning in. Do drop in your thoughts in the comments section of this video.